now that we know that there will be light emerging from slit 1 and slit 2 over here, and they overlap in this region, let's try to find specific points that are constructive. Let's try to find specific points that are destructive, and from there we try to determine the defining characteristics for constructive interference and destructive interference in terms of its path difference. Okay, so before I go further, let's make sure everybody understand this diagram here clearly. So we have light wave emerging from slit 1 and light wave emerging from slit 2 over here. They're in green and in blue just to differentiate them, saying that they are from different slits. So we should see these lines here as actually the wavefront of the circular wave or the spherical wave. So wavefronts actually means that they are lines that connects all the points with the same phase. Okay, so in here I'm drawing the wavefronts only for the crest only, so you can think of it as wave traveling out, but any point that you see this green line over here will be the point where you meet the crest. Then any point in the middle between these two green lines will be a trough over here. So you can think of it as a wave, crest, trough, crest, trough, crest, trough, crest, trough, crest, trough. The same idea for the blue over here is also every time you see a line, a blue line, it means your blue wave, not blue color wave, just blue, the blue slit 2 wave, it's at its peak. Then every time you reach the midpoint between two lines, that means you are at the trough for the blue slit 2 wave. Then you have peak, trough, peak, trough, peak, trough. Okay, so that's the idea of the wavefront that I'm trying to represent here. Okay, so now let's try to understand how do we get constructive, which point do we get constructive, what can we say about its path difference. So here I'm going to pick a specific point called point X, and what I'm going to study now is I'm going to tell you, for now, I'm just going to tell you that because you see here, it is the intersect of the blue wavefront and the green wavefront, right? Just now I say that every time you see the wavefront, it means that the peak arrives at that point. So if you see that the slit 1 wave arrives at here with a peak, the slit 2 waves arrive at here also with a peak, then its peak meets peak, right? So what I'm going to know is that at this point X over here, constructive interference will occur because they arrive at the same phase, peak meets peak. So later on it will be a trough meets trough, trough meets trough, later on it will be peak meets peak, later on it will be trough meets trough. So it will be an in-phase kind of relationship that happens at point X over here. So the resultant displacement or the resultant wave will be maximized over here. It's a constructive interference. But now I want to focus on the path difference or the length difference for these two light waves to arrive at point X. Path difference means by light is going to travel, this green light, not green color light, this green slit 1 light is going to travel from slit 1 to X. So we can call this line over here to be the distance that needs to travel from slit 1 to point X. At the same time, there will be this blue slit 2 wave coming from slit 2 and arrive at X as well. So the distance will be from slit 2 to X. What I'm going to study right now is the difference between the path length of these two sources right now. Okay, to keep it simple, I'm going to pull out this light wave over here. What I'm going to determine here is what's the difference in the length between this green path and this blue path over here. What's the difference in their path length, or you can call it as length difference, or you can call it as path difference. Okay, so it's a counting game right now. So let's calculate. Let's count with me. So it starts with a trough over here, right? So if it starts with a trough, then you go back to a trough. Then this is 1 wavelength done, right? So this is 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength, 6 wavelength, 7 wavelength, 8 wavelength, 8.5 wavelength. 8.5 wavelength because it doesn't reach a trough over here, it reaches a crest, so that's only half of the wavelength. So over here, it takes 8.5 wavelength for you to go from S1 to X. Okay, how about S2? Okay, I'm going to call this as R1 now, means by the path from S1 to X. R2 will be the path from S2 to X. So focusing on, where did they calculate R2? Okay, R2 is 11.5. Let's try to check it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and a half. 11 and a half. So it takes 11.5 wavelength for you to go from slit 2 to X. So that's R2. So R2 is 11.5 wavelength. R1, we're going to minus with R1. R1, actually we calculate it just now. Let's calculate again. 1, 2, 3, 4, 5, 6, 7, 8 and a half. So 8 and a half wavelength for you to go from slit 1 to X. So you can see that the path length from S2 to X is 11.5 wavelength. The path length to go from S1 to X is 8.5 wavelength. And the path difference or the length difference between these two sources to arrive at point X will be 3 wavelength. Okay, so this is what you can see. For point X, the path difference is 3 times the wavelength. And we know that at this point, just now we already discussed, it's a constructive interference that happens over here. I'm not going to make any conclusion. I'm just going to say that here constructive interference occurs. At the same time, the path difference is 3 lambda. Okay, now let's move on to another point maybe. Okay, let's point to point Y. Okay, point Y over here, you can see that for the slit 1 wave, the green wave over here, the slit 1 wave will arrive at this point with a trough because this point Y here is exactly between this wavefront, this green wavefront, and the next green wavefront. It's exactly in the middle. So you know that slit 1, the wave that arrives at here will be a trough. Okay, how about the blue slit 2 wave? The blue slit 2 wave will arrive at here, and you arrive at here in between this blue wavefront and the next blue wavefront. So it's in the middle. Again, you say that the slit 2 wave will arrive here at the trough as well. So slit 1 arrive at the trough, slit 2 arrive also at the trough. So trough meet, then later on it will be crest, later on it will be trough, later on it will be crest. So this is also an in-phase situation. And as we discussed earlier, if it's an in-phase, if they arrive in phase, what will happen is the way they superpose, the way they interfere, the way they overlap will cause a maximized kind of resultant wave. So you can say that at point Y here, you should also expect a constructive interference to occur. So it's the same as point X, but point X over here in this diagram is peak meets peak, but for point Y in this diagram is trough meets trough. But still, it's still in they arrive in a phase. So because they arrive in phase, it will be a constructive interference. Now we know that it's constructive. Let's try to find the path difference as what we did before. So of course you have your green path here, you have your blue path here. You want to find the difference. The green path here you call it as R1. The blue path here you call it as R2. We are going to find R2 minus R1. So let's start with R2 first. R2 you can try to count. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 we still haven't go up because right in the middle you reach the trough. So this is exactly 11 wavelength for R2. Let's try to do it for R1. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you haven't go up yet. This is 9 wavelength, exactly 9 wavelength. So this is R1, 9 wavelength. So if you find the path difference between the two, you get the answer to be equals to 2 wavelength. So the difference in the path length between S1 to Y and S2 to Y is exactly 2 times the wavelength. Okay, and again we mentioned just now, this one is trough mid trough. This is a constructive interference that will happen at this point as well. Okay, not making any conclusion, just telling you what I observe. Okay, so R2 minus R1 is 2 lambda, at the same time it's constructive. Next, let's pick another point, point Z over here. Point Z over here, if you look at the green slit 1 wave, you'll see that point Z here is right between this green wavefront and the next green wavefront. So we know that the slit 1 wave will arrive here at the trough. But what about the slit 2 wave? The slit 2 wave will arrive at this point where you can see there's a blue wave front passing exactly through Z. So you know that the blue slit 2 wave will arrive at here with a crest. So this is a green trough meeting a blue crest. So this is crest meet trough. So they are anti-phase with each other. Their phase is opposite to each other. In this case, we should expect a destructive interference because crest meet trough, they will cancel each other out. Trough meet crest, they also cancel each other out. So at this point, you should also expect a destructive. You will now expect a destructive. It's not the same as earlier. Earlier, these 2 points were constructive, but now this point is destructive interference. Now let's try to determine the path difference as earlier. Then from there, maybe we can get a bit of insight to what happened. Okay, so we are going to have this green path and this blue path, and we are going to find the difference between the 2 paths. So we are going to start with finding R2 first. R2, we have 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength, 6, 7, 8, 9, 9.5 wavelength for R2. How about R1? R1 you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is 9 wavelength for R1. It arrives at the trough, not crest, so we count until here. So this is 9 wavelength. So if you find the difference, you get that the difference is 0.5 wavelength. And again, this is a destructive interference. So maybe at this point, you can sort of form a conclusion to what we can observe here. You can see if it's constructive, right, the path difference is always an integer multiple of wavelength. It's always a multiple of 1, 2, 3, 4, an exact number, an integer. But if you talk about destructive interference, if you find the path difference, you see that it's always coming up with a 0.5 wavelength. It can be 1.5, 0.5, 3.5. And if you think about it, it actually makes sense. Because if you start with a trough, you go for, let's say, 8 wavelength to reach here, then you also arrive at the trough because if complete exactly 8 wavelength, so you arrive at the trough as well. If you complete 8.5 wavelength, let's say, you start from a trough. If you go 8 wavelength, you arrive at the trough. But you have another 0.5 wavelength, it will change you to become a peak. So if you have one path that has 0.5, another path that has no 0.5, so the difference will be definitely there will be a 0.5 for its difference. So if there's a 0.5 for its difference, it just means that one of the wave arrives at the crest, one of the wave will arrive at the trough. So therefore you get destructive interference. Okay, so the conclusion that I can make over here is that if it's constructive interference, R2 minus R1 must be an integer multiple of the wavelength. Okay, it can be 2, it can be 3, it can be 4, it can be anything. Okay, but it has to be a integer number. It cannot have any decimal places. Okay, if you think about constructive interference, it makes sense because let's say if you start with a trough, you travel 8 wavelength to arrive at point X, let's say. So 8 wavelength means by you end up with a trough at point, let's do point at X because X is a peak. Let's point at Y. Okay, let's talk about Y. Okay, so let's say S1 takes 10 wavelength to arrive at here. If it starts at the trough, you complete 10 wavelength. When you arrive at Y, you should also arrive at the trough as well, because you complete from trough. 1 wavelength you arrive at the trough, 2 wavelength you arrive at the trough, 10 wavelength later you arrive at the trough. Okay, but let's say S2 is 12 wavelength, so if you start at the trough, you also end up with a trough as well. So if it's trough meets trough, then it's constructive lah. So if this one has no 0.5, this one also no 0.5, then if you minus it out, then you get an integer multiple lah. Okay, even if you have 0.5, if S1 you have 8.5 wavelength. So let's say if you start with trough, 8.5 wavelength later, you end up with a peak. Because 8 wavelength, you stop at the trough, but add on a 0.5, so you change from trough to crest. So 8.5 wavelength, let's say you arrive at the crest, 10.5 wavelength, 10.5, you travel 10, you arrive at the trough, but at 0.5 you become a crest. So it's crest meets crest kind of situation. So crest meets crest is constructive. Okay, so if R1 and R2 both has a 0.5, if you minus it out, there will be no 0.5. So there will be no 0.5 for its integer multiple. Okay, it's a bit complicated to explain like this. You have to sort of look at the figure, think hard about it to understand the idea. Basically, if you have crest meet crest, R1 and R2 both will have 0.5 or both will not have 0.5. So if you minus it out, there will be no 0.5. If it's trough meet trough, both of them will either not have 0.5 or have 0.5 together. So if you minus it out, there will be no 0.5 also. So that's out the explanation. Destructive interference, you have a 0.5 definitely at the back. You need a 0.5 because it means by source 1 travel a certain distance, source 2 also travel a certain distance, but maybe add on an additional something 0.5 wavelength. Because you have a 0.5 means by S2 is going to travel, S2 is going to change from a crest to a trough, or it's going to change from a trough to a crest. So if S1 doesn't change but S2 change, so it means one will have to be a crest, one will have to be a trough. So if they meet up, they should destructively interfere. Okay. So that's the idea of constructive interference. If you see constructive interference, the path difference should be equals to m lambda. M can be any integer. If it's destructive interference, it should arrive at m plus half lambda, because plus half here represents that it switched from a crest to a trough. So if two of the wave coming out with a trough, one will end up with a crest, another one will remain as trough. So trough means crest, destructive. If both of the wave coming out with a crest, because one of them has a 0.5, so one of them you change to a trough when it arrives at this point. Okay, so crest meet trough again is destructive. Okay, I'm not specifically mentioning x, y, or z. I'm just saying a random point. Okay, so that's the defining characteristics for constructive interference and destructive interference. One is equals m lambda, one is equals m plus half lambda for its path difference. Okay, so now that you know that, let's say if we place a screen at this point over here, let's try to observe what would happen. Okay, if you place the screen over here, let's try to make it slightly translucent. You see that at certain points on the screen, you can see that the blue wavefront meets with the green wavefront. So this point here, we can call it as constructive interference. Okay, you can see points like this over here as well. So this is constructive because blue wavefront meets the green wavefront. Points like this is also constructive. Points like this is also constructive. Points like I think you see it. There points like this, okay, near somewhere here you can see blue meets green as well. So you can see these points here are constructive interference, where you can see peak meets peak, peak meets peak, peak meets peak, peak meets peak, peak meets peak. Okay, so these are constructive interference. You can also see certain points where you can see the green wave is a trough because it's in between the two wavefront, but the blue wave is a peak. So this is peak. Green trough meets blue peak. So this is destructive. This is green peak meets blue trough. This is destructive. This is blue trough, a blue peak meets green trough, destructive. This is green peak meets blue trough, also destructive. So you can see that the point where constructive interference happens will alternate with the points where destructive interference happens. So you have the center, which is constructive. Center is always constructive because the distance for you to go from here to the center and from here to the center is the same. So if the path difference is 0, it's constructive, right? So the center is always constructive, but after that you will see destructive, constructive, destructive, constructive. They alternate with each other. So this is what you can observe if you place a screen over here. And because constructive is supposed to make it enhance, you see a bright spot over there. Whereas for destructive point, you will see that they are cancelling each other out. So you will see no light at this point over here. So bright light, no light, bright light, no light. So what you can see actually is an alternating bright and dark fringes. Fringes are just lines of light. Okay, lines of light. So you can see alternating bright light, dark light, bright light, dark light, bright fringe, dark fringe, bright fringe, dark fringe, bright fringe. They are alternating with each other. Okay, so this is what you can observe on the screen if you place the screen somewhere far away from the double slit. You see it as the center being a bright fringe, and you have alternating bright and dark fringes on both sides of the central fringe. Okay, so this is what you may observe if you're carrying out a Young's double slit experiment in this setting over here. Okay, so if you want to think about it in terms of path difference, of course at the central, the distance from S1 to central, distance from S2 to central, they should be equidistant, right? Okay, because it's in the middle, equidistant. So this one is 0 lambda for its path difference. Then moving on to the destructive, you get 0.5 lambda. R2 minus R1 is 0.5 lambda. R2 minus R1 is 1 lambda. Okay, so it means that if here you take 12 wavelength, let's say, here you might take 13 wavelength. Okay, for here, if here you take 13 wavelength, then maybe here you take 15 wavelength. The difference in wavelength is 2 wavelength. The difference in wavelength is 1 wavelength. Okay, so this is it being expressed in terms of path difference. With the center, definitely no difference in path. Then the path difference you get larger and larger. And you see different points where if it's destructive, you get 0.5 for its path difference. If it's constructive, you get an integer number for its path difference. Okay, so this is what you can see in terms of path difference. Okay, in terms of brightness, what you can see is that you can see the central here to be a bright light. So I here represents intensity. So at the center, you see a bright, intense light over here, but it dims off when you reach this spot over here, this distance over here, it will be a dark fringe. Then after that, the intensity become maximum here also. So here you get bright fringe. Here the intensity drops to 0, so it will be a dark fringe. Here it will be a bright fringe. This is a graph with its y-axis over here, x-axis over here. So y-axis represents the intensity, x-axis here represents the distance from the center. Okay, so it goes from bright to dark, bright to dark, bright. Here also it goes from bright to dark, bright to dark, bright to dark. Okay, so this is what you can imagine in terms of brightness. Bright, dark, bright, dark, bright. Okay, so yeah, that's what you can observe in terms of brightness on the screen. Okay, later on we are going to put everything here in the form of equations. How we are going to relate the distance between the screen and the slit, how you do this relate the distance between the slit, and also this distance over here, how do you relate them in terms of equations. But we leave that to the next video.